previously we talked about the discovery of the 3 subatomic particles. We talked about electrons, we talked about protons, and then we also talked about neutrons. We talked about the charge that each of these have. The electrons, we said, had a -1 charge. The protons had a +1 charge. Then they couldn't account for the mass, so this led to hypothesizing that there was another subatomic particle, and eventually the neutron was discovered, and this was found to be electrically neutral. So today what we're going to look at is how these subatomic particles can tell us something about the element. Specifically, we're going to be looking at the mass, and then we might start to look at the charges. So let's go ahead and start our discussion on atomic numbers. So one of the things we want to note is that elements differ from one another according to the number of protons in their nuclei. So we denote the number of protons using the atomic number. So whenever we see Z, this is just another way of saying the number of protons. Okay, so, and this is if you have 5 different atoms of hydrogen, each one of them will contain 1 proton in the nucleus. So the number of protons defines what your element actually is. Next thing that we're going to look at is the mass number, and we'll denote that with a capital A. So this is equal to Z plus N. So Z we just defined as the number of protons, and N is your number of neutrons. Okay, so we haven't included electrons in here at all. So if you'll recall from the last lecture, we said that the mass of the proton is essentially equal to the mass of the neutron. Well, now what we need to see is that the mass of the electron is actually quite a bit smaller than the mass of the proton and the mass of the neutron. In fact, the mass of the electron is about 1/2000th that, not 1/20,000th, 1/2000th that of the proton or the neutron. So that tells us that we would need approximately 2,000 electrons to equal the mass of 1 proton. So let's go ahead and take a look at how we write some of these chemical symbols. So here are the 2 main ways that we'll see symbols represented. This way right here on the left, this is how we'll find the symbols on the periodic table. And then over here on the right, this is how we'll find these symbols in text. Okay, so the X in both of these cases, the X right here is our chemical symbol. And each element has a unique chemical symbol. And then on the periodic table, we'll have Z, which tells us the number of protons, or it's the atomic number. And what we'll find is that whenever we write a chemical symbol out, for instance, let's look at chlorine 37. Okay, so we have chlorine 37 here. So 37, that corresponds to our mass number. So that's our mass number, and that is going to be equal to the number of protons plus the number of neutrons. So what we could do is we could go through and we can make a list. So sometimes we'll write it out like this. We'll either use a Z or an N and write out the number of protons, electrons, and neutrons for each element. So if you can do this, we would say that you are a Zen master. So chlorine has 17 protons. And then since there's no charge on this, that would mean that there are 17 electrons because it's electrically neutral. So since we have 17 positively charged protons, we have to have 17 negatively charged electrons. And then the number of neutrons, well, since the mass number is 37, the number of protons is 17, that means our number of neutrons must be 20. So we can go through and find the number of protons, electrons, and neutrons for any element if we know the mass number. Something that I'd like to point out is that this Z, whenever we're writing out the chemical symbol, this is redundant. So we could actually write this out as chlorine 37. Or another way you'll see it written is like this, chlorine 37. That 17 is redundant. That tells us the number of protons. Well, the chemical symbol also tells us the number of protons as well. All right, so let's go ahead and look at an example. So our next topic that we're going to talk about with respect to these subatomic particles is an isotope. So an isotope will be something that, so if we are comparing two isotopic species, okay? So we have two isotopic species. By definition, these will have the same number of protons, but a different number of neutrons. So they're both going to have the same number of protons, so they're going to behave in a similar fashion, but they're going to have a different number of neutrons. And we'll look at a few examples in just a minute. Let's go ahead and look at this example here. So the isotope of uranium used to generate nuclear power is uranium-235. How many protons, neutrons, and electrons does an atom of uranium-235 have? So let's go ahead, and you can either use a Z or a P for this and figure out how many protons, electrons, and neutrons we have. Okay, so recall that our chemical symbol, we have our mass number up in the left superscript, and then our atomic number in the left subscript. So we know we have 92 protons. Since we're neutral, there's no charge indicated on this, we have 92 electrons. And then to find the number of neutrons, we would take 235 minus 92, so we would have 143 neutrons. So you should note that in all cases this is true. If the species is neutral, your number of protons is going to equal your number of neutrons. All right, so let's look at a series of isotopic samples. So let's look at hydrogen 1, hydrogen 2, which we'll call heavy hydrogen or deuterium, or hydrogen 3, which we would call tritium. So what we want to do is let's go ahead and compare the number of protons, electrons, and neutrons in this series of isotopes. So all of these are hydrogen atoms, so they all have one proton. They all have no charge, so that means our number of protons and electrons have to be equal, so they all have one electron as well. But where they differ is they have a different number of neutrons. So in this first one, the mass number is 1. We have 1 proton, so there are no neutrons. Now for deuterium, we have a mass number of 2. We have 1 proton, so that means we have 1 neutron. And then for H3 here, or tritium, we have 2 neutrons. So note here that for isotopic species, the only thing that is differing from isotopic species to isotopic species is the number of neutrons. Protons are staying the same. So the last thing we probably need to talk about here with respect to what can be found on the periodic table is we've talked about where we get the atomic number, which is the number of protons, but then we have these mass numbers. So whenever we were looking at these isotopic samples, we said uranium-235. But if we look at some of the masses on the periodic table, they all have a different number of decimals, and there's really not anything that is measured as 0.00. So what we want to do is we want to figure out how these average atomic masses are actually calculated. So experimentally what they do is they'll use a mass spectrometer, which is an instrument that is used and it's able to separate out the different masses more or less a really simplified approach about this is to think about if you had two different masses and you were erasing them. They both started with the same amount of energy. You could figure out which one was finishing faster. So what we'll see is that the atomic mass that we're reporting, the average atomic mass, is a weighted average. It's not the average. So even though there are two isotopes of chlorine, there's chlorine 35 and chlorine 37, whenever we look on the periodic table, it tells us that we have an average atomic mass of 35.45, which is not the true average of chlorine 35 and chlorine 37. So it's a weighted average. So we have to take into account the fractional abundance, or how much of each element is present. So the way that we find these weighted averages is we have to find, we're going to take the sum. So for our atomic mass, what we'll do here is we'll take the sum of F sub I times M sub I. Okay, so the I just indicates, that's an index, and that tells us which isotope we're talking about. The F here is the fractional abundance, or you could do the percent abundance and then divide by 100 later. And then M sub I will be your mass of your isotope. Okay, so let's go ahead and look at this example. So neon has three isotopes: neon 20, neon 21, and neon 22. So you are given the mass of each isotope here. So this is M sub I. And then down below, I actually go through and I give you the percent abundance. So if we want to find the average mass of neon, what we're going to do is we have to take a sum of these, of the fractional abundance times the mass of the isotope. So whenever we're converting 91.84% to a fraction, we'll have 0.9184, which won't have any units, times the mass of the isotope, 19.9924 AMU. Plus, so up here, whenever I gave you this summation sign, this capital sigma, that just means take the sum. So we'll have our next fractional abundance will be 0.0047 times the mass of the isotope, 20.9940 AMU, plus fractional abundance of our final isotope of neon 22, which is 0.0769 multiplied by that mass of the isotope, which is 21.9914 AMU. So then what you'll do is you'll plug and chug, plug that into your calculator, and we would get an average, weighted average atomic mass of 20.151 AMU. So these values might differ slightly from what's on the periodic table. It depends on the year that the data was pulled from, the fractional abundance if we're including all isotopes or just the major contributors. But you should end up getting something close to what's on the periodic table. So this concludes our first discussion on looking at some of the subatomic particles. Next time we'll start to look at chemical formulas, and then we'll start to look at why things are arranged on the periodic table the way they are and some different notations that we'll use.